All right, continuing 3.4a. So we talked about some properties and some postulates in the last 3.4 video. So now let's go a little bit deeper with those. Let's open this thing up. So we were given 3 statements, and we were asked to determine whether these statements are sometimes, always, or never true. So the first one, if plane T contains lines EF and line EF contains point G, then plane T contains point G. Okay, so let's draw a picture to make sure we're understanding what this thing is telling us. So if plane T, so we draw our plane, okay, and we label this plane T. If it contains line EF, okay, so that tells me I've got to have a point E and a point F on this thing. And then line EF contains point G, so there's another point on here. Got to be point G. Then plane T will contain point G. So as we see, there's no situation that I could draw this picture and G not wind up being in the plane, because the entirety of this line must lie in this plane according to our postulates. So this is always going to be true. Okay, let's look at our next statement. Line GH contains 3 non-collinear points. Okay, well, from the get-go, line GH can only contain points that are collinear. So there's no way for a line to contain points that are non-collinear. So that's going to be never true. I can't even draw a picture for that. Okay, this next one. If line AB and line HK are coplanar, then they intersect. Well, so let's think about this. So if I have a plane drawn on here, and so let's say I have my line, I have a line A, B, and this could maybe be my line HK. Well, in this scenario, they are intersecting. But I could also, if I wanted to, instead, draw the picture of where these 2 lines, they could maybe be parallel to one another, and thus they would never intersect. So for this one, if AB and HK are coplanar, then can they intersect? And the answer is going to be sometimes, because we could have a time when they could be intersecting or could be parallel and they never intersect. Okay, let's keep moving on. Okay, so down here, we're asked to state the postulate that can be used to show each statement is true. Okay, so we're given this figure to work with. So first statement is E, B, and R, so the points E, B, and R are coplanar. So we're asked to basically go through and determine which postulates could help us to determine if that's true. So if we flip back to our postulates for just a second. So we've got 3 non-collinear points. That's what E, B, and R were. So if we look right here, numbers 2 and numbers 4 kind of tell us something about 3 non-collinear points. So number 2 tells us for any 3 points not on the same line, or non-collinear points, there's exactly 1 plane. Number 4 tells me a plane contains at least 3 points not on the same line. So in our picture, we were asked to describe about E, B, and R being coplanar. And so that can be true. We could indeed draw a plane. The plane that's on here right now would actually not work for us, but we could draw a plane that could contain E, B, and R if we wanted to. And so that would be postulates 2 and 4 would help us to show that statement to be true. Okay, the second one, B, D, and W are collinear. So let's flip back to our postulates. Here we go. So E, B, and W, or excuse me, B, D, and W, excuse me. So those 3 points were collinear. That's what they appear to look like. So 1 and 3 deal with collinear points. Okay, so number 1 says for any 2 points, there's exactly 1 line. And then number 3 says a line must contain at least 2 points. So if we're going to go through and prove and show that this statement can be true, then we need to know about postulates 1 and 3. Okay, let's keep moving forward. Okay, so now we're going to kind of introduce you guys to the concept of writing 2-column proofs. Okay, so there's 2 main types of proofs. There are paragraph proofs and there are 2-column proofs. And we're not really going to worry about the paragraph proofs for this unit. We're just going to deal with the 2-column proofs. So let's look at this one right here. So solving for x and show every single step. Okay, so I just went through and I solved this thing the way we normally would solve a multi-step equation. So 2x plus 18 equals 6. First, you want to subtract 18, get the 2x alone. And so then you'd have 2x is equal to negative 12. You want to get the x alone. So you divide by 2, and you wind up with x is equal to negative 6. So now, where the proofs is going to come in is also justifying where we get each step from. Okay, so this first statement, 2x plus 18 equals 6, my justification for having this step is that it was given to me. Okay, so then I go through and I do some subtraction action, and then I get down to 2x is equal to negative 12. And the reason why I have this statement right here is because of the subtraction property. Okay, I had two things that were equal, 2x plus 18 and 6. I subtracted the same thing from them. I subtracted 18, and I wound up with 2x and negative 12, and those two statements are equal to each other, and that's true because of the subtraction property. Okay, next up, then 2x is equal to negative 12, divide both by 2, and I get x equal to negative 6. So the reason why I have this statement, x equals negative 6, is because of the division property. 2x and negative 12 were equal to one another. I divided them both by 2, and I wound up with x is negative 6. All right, so that was kind of an informal proof. Let's look at some actual proofs now. Okay, so we're looking at this proof. We're asked to prove that if 3x minus 4 is equal to 26, then x is equal to 10. So whenever we start with these things, we're always going to look at the stuff between the if and the then. If we're given an if-then statement, so our hypothesis, the stuff between if and then, that's always going to be my first statement. So 3x minus 4 is 26. We'll put that as our first statement. And with each statement, we're going to have a reason for us having that statement. So the reason why I have 3x minus 4 is 26 is because it was given to me. So now I'm trying to eventually get down to solving for x. So first thing I'm going to do is I'm going to add 4. So I add 4 to both sides, and I wind up with 3x is equal to 30. And now I have to write the reason that I got from statement 1 to statement 2, and that was by using the addition property. I added 4 to two things that were equal, and so the resulting sums were equal to one another. Okay, lastly, I want to finish it out. So I'm going to divide both sides by 3, and I wind up with x equals 10. And so how did I get from statement 2 to statement 3? By using the division property. Okay, let's look at another one. Prove that if AB is equal to CD, AB is equal to 4x plus 8, and CD equals x plus 2, then x equals negative 2. Okay, so again, we are going to start by looking at everything between the if and the then. And this time, we've got a lot of stuff. So everything between the if and the then, which is AB is equal to CD, AB is equal to 4x plus 8, and CD is equal to x plus 2, that is all our given statement. That's what we have to work with at the beginning. Okay, so eventually I know that I'm trying to work my way down to proving that x is equal to negative 2. So first up, I have to set up some kind of an equation so that I can solve for x. Okay, so I'm told in my given statement that AB is equal to CD. And then I'm also given that AB is 4x plus 8 and CD is equal to x plus 2. So what I'm going to do, I am going to take the first part of my given statement and I am going to rewrite it down here. And that'll be my second statement. So AB is equal to CD. I'm just rewriting it. AB for 4x plus 8, and then I'm putting in x plus 2 for CD. Okay, so I knew that AB is equal to 4x plus 8, so anywhere there was an AB, I could replace it with 4x plus 8. CD was equal to x plus 2. Anywhere there was a CD, I could replace it with x plus 2. So this is me using the substitution property. Okay, so now that I've got a multi-step equation set up, I'm going to go through and I'm going to solve for x. So first thing I would do is I'm going to get all my x's on one side, so I need to subtract an x from both sides, and I wind up with 3x plus 8 is equal to 2. And the way I got from statement 2 to statement 3 was by using subtraction property. Okay, next up, I want to get 3x alone, so I'm going to subtract 8. So now I have 3x is equal to negative 6. And the way that I got from statement 3 to statement 4 was by using subtraction property. Lastly, I want to get x alone, so I'm going to divide by 3. So I wind up with x is equal to negative 2. How did I get from 4 to 5? By using division property. Okay, once you kind of see a couple proofs, they start to come a little bit quicker. Okay, so now we got this last one. This one is a little bit weirder looking. So let's look at it. So prove that if v is equal to 1/3 pi r squared h, then h is equal to 3v divided by pi r squared. Okay, so for this one, we see that between if and or then, we have that, so that's going to be our first statement. And as you might have noticed by now, a pattern starting to form. Our first reason is always going to be given. That's what our first reason will always be in any proofs that we write. So now we have to think through, what are they actually asking us to do? Okay, so they gave us an expression that was equal to v, and then they want us to move it around to where now the expression will be equal to h. All right, so let's see, how can we start to kind of move some stuff around? So this is what we're starting with. We know that eventually we need to have 3v. So we've got v is equal to 1/3 pi r squared h. So two ways you could think about doing this. You could either think about this as you are going to multiply both sides by 3. So that is, you put a 3 in front here, and you put a 3 right here. Then you'd have 3 times 1/3, which would just be 1, which is, we don't have to write the 1. And then 3 times v would be 3v. So you can either think of it as we're multiplying by 3 or we're dividing by 1/3, same thing. So to go from statement 1 to statement 2, you're using multiplication or division property. Okay, nextly, we need to do 3v divided by pi r squared. So I'm going to divide both sides by pi r squared. And once I do that, I'll have 3v is equal to pi r, or 3v divided by pi r squared is equal to h. And the way I got from statement 2 to statement 3 was by using division property. Okay, and then lastly, this last one is kind of a nitpicky one, but we do have a property for it. We have currently 3v divided by pi r squared is equal to h. They want us to end with h is equal to 3v divided by pi r squared. So we're able to do this. We're able to just switch the sides and rewrite it as h is equal to 3v divided by pi r squared. And we can do this by using our symmetric property. So again, that one's kind of a little nitpicky one, but to get it in the right order, we can just use the symmetric property.